Oh, phooey. Ah, shoot. Sorry. So e to the negative n, and then n squared. Yeah, you got it, right? N, let me use my red pen because this is what I would use on your test from time to time. N squared. I hope this didn't cause any confusion. I don't think it did. Well, you can yell at me if it did. All right, and then last but not least, whoops, last but not least, I'm gonna make an n squared here and an e to the n. Thank God you guys are patient with the young and talented Mr. Ripley. I'm gonna turn this guy into a black again. All right, now watch. I'm going to list the first two terms because I know that this thing increases from 0 to 2. So I'm going to turn this into negative 1 to the 1 squared over e, plus negative 1 squared times 2 squared over e squared. You see what I did? I just took out the first two terms, plus the sum as n goes from 3 to infinity of negative 1 to the n, n squared over e to the n. See that little trick? I removed a finite number of terms. Clearly, these add up to a number. They converge. These converge. It's finite. And I just showed that this decreases from n equals 3 to infinity. So here's our final little statement. Since 1, the limit as n goes to infinity of the sum as n goes from 1, whoa, let's try that again. Limit as n goes to infinity, I'm a little crazy right now, aren't I? N squared over e to the n equals 0, and b sub n plus 1 is less than or equal to b sub n for all n greater than or equal to 3. See what I did there? I just grabbed this guy. That implies that the sum as n goes from 1 to infinity of negative 1 to the n squared over e to the n converges. I just proved it converged. All right, now that's a lot of work. That's a lot of work, but really for this series, it's kind of the only thing that you can do. All right, you gotta show that, and it's an ugly looking series. Yeah, I mean, you'll see ugly series where your hands are sort of tied, but if you really think about it, well, the coolest part is we got to use all of our calculus. We got to use our differential calculus. I guess we didn't get to take integrals, but don't worry, we'll get to do that too. We got to use L'Hopital's. Everything is fun. All right, so let's go ahead and figure out how to approximate these values. We've played with remainders a little bit. Remember that back when we were talking about integral tests and comparison tests and all that good stuff. So let's remember, we know that the sum, which is equal to the limit as n goes to infinity of s sub n, is equal to s sub n plus r sub n. And this guy is referred to as the remainder, or if you think about it, it's the error term if we stop at n, right? So s equals s sub n plus r sub n. Now let's think about what an alternating series does, because this one's actually really easy to play with. Watch. So let's get ourselves oriented first and foremost. We're talking about an alternating series. This only is true for alternating series, okay? This will be so bad. Now again, remember this could be plus 1 if we wanted to. It doesn't really matter. In fact, let's make it to the n plus 1 so we're dealing with positive terms. It'll make our, sort of conceptually it'll be a lot simpler because my first term is going to be positive. All right, so let's think about our first term. This is going to be b sub 1, right? That's my first term that comes shooting out of this thing. But this also happens to be s sub 1, correct? Now, what happens? Well, I take b sub 2, so I'm going to have minus b sub 2. And if b sub 2 is less than b sub 1, then when I subtract, let's say that this distance right here is going to be b sub 2, right? So I subtract b sub 2 from b sub 1, and what I get is s sub 2, right? Now let's change. And then what happens? Well, then I go plus b sub 3. But b sub 3 was less than b sub 2, right? So here we go. I'm going to end up, this guy right here is going to be b sub 3, right? Does that make sense? Okay. And then, well, what happens? We end up with s sub 3. All right. Now, what are you noticing? S1, S2, S3. Let's do one more little thing right here. Do it in green. Minus B sub 4. So the distance from, let's say that this distance, I'm going to have to cheat and come down here a little bit. Let's say that this distance right here is B sub 4, which I'm going to subtract from S sub 3, and that's going to give me S sub 4 right there. What do you notice is happening? What's going to end up happening with this is that it's going to end up going doink, 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 and it's going to act just like a target. It's going to zoom in on S, right? Doesn't that make sense? Go out to S sub 1, S sub 2 is over here, S sub 3 is over here, S sub 4, S sub 5, S sub 6, and then I'll get closer and closer and closer to S. Now, let's zoom in on a little sliver right now. So let's say, for example, that S lives here. And this is going to be B sub n. All right, because remember, what we're trying to do is we're trying to figure out how far off we are. We can estimate, we know that B sub n is an estimate for S, right? I mean, set n at 10, go out and do some addition and subtraction, and that's your estimate for what S is, right? But look, check this out. If I come across to B sub n, whoops, I don't want this to be B sub n, I want this to be S sub n. If I come across to S sub n, then I know that this guy is going to be S sub n plus 1, and this length is going to be B sub n plus 1, right? Because we're subtracting or we're adding, it doesn't really matter. We can jump either way. We can go in either direction if you think about this, right? Okay, so think about that. Do you agree that by this equation right here, I know that S equals S sub n plus R sub n. So R sub n is always going to equal S minus S sub n, correct? So here's S sub n. Do you agree that that distance right there is going to be R sub n? What do you notice about R sub n with respect to B sub n plus 1? R sub n, as long as the series converges, if it doesn't converge, it doesn't make sense to talk about a remainder in terms of how far off the sum you are, because you're going to blow up to infinity anyway. R sub n is always going to be less than or equal to B sub n plus 1. Actually, theoretically, it's less than. Excuse me. Now, the way in which we write this is R sub n, absolute R sub n. That we get used to seeing this as an error term. All right? When you see it as absolutes, that's a distance, and it should tell us that it's an error. I'm sorry, you guys, I'm trying to get over a cold here. So R sub n is always less than or equal to B sub n plus 1. Now look at it again. Make sure that you believe me. R sub n is the distance between S sub n and S. B sub n plus 1 is always, it's the next term. And when I add it to S sub n, I get S sub n plus 1. So this distance is always going to be greater than or equal to R sub n. And that distance, we already know, is B sub n plus 1. So this is called the error estimate for alternating series. So useful, so helpful, because it tells us how close we are to the absolute value. Did I say absolute value? To the actual value of the sum. That's why alternating series are so powerful, because not only can we determine whether they converge or diverge, but we can automatically tell how close we are to the actual sum, which makes it really, really useful. All right. Now, we're going to get a little crazy here. I think you'll like this. This next little term is something called absolute convergence. Absolute convergence. Super powerful. Even though it feels really weird. I always have students who are like, what? Why are we doing this? Well, the absolute convergence, and there's actually a test for it. We're going to say the absolute convergence test. All right, so if, you ready? Here we go. The sum as n goes from 1 to infinity of the absolute value of a sub n. If this thing converges, if this converges, All right, so if this series, when I put absolute values around something, if this guy converges, then that implies that the sum as n goes from 1 to infinity of a sub n also converges, but it doesn't just converge. There's something more powerful. It converges absolutely. All right. Now you may go, Ripley, what? What's this absolutely and absolute convergence and all that good stuff? Well, what it has to do with is a strength of convergence. So, for example, watch. If I take the sum as n goes from 1 to infinity of -1 to the n plus 1 times 1 over n squared. Now, I want to make sure you understand something here. Absolute convergence it's a new idea, but it's really not. It's really, what it actually is it's a new tool. It's something that we can use to simplify our lives down the road. Now, clearly this is an alternating series, so we could use alternating series tests. The problem is that alternating series tests can sometimes be a ginormous pain in the butt. All right? So, watch. I'm going to say this. Since I know that the sum as n goes from 1 to infinity of 1 over n squared converges. Why? How do I know that? Well, because it's a p series, right? I know that p is greater than 1. By the absolute convergence, and I'm not going to get lazy, all right? Since the series of 1 over n squared is equal to the absolute value of -1 to the n plus 1 over n squared, and 1 over n squared converges, we know that the sum as n goes from 1 to infinity of -1 to the n plus 1 over n squared must also converge. But not only does it converge, it converges absolutely. It's a powerful tool. What it enables us to do is remove negative terms from a series and check to see if it converges with those negative terms missing. Okay? I'm gonna give you another example here. I'm gonna give you 2 examples. Now, you may say, well, if is the converse true? If a series converges, then won't the absolute value of that series converge? Absolutely not. No pun intended. So think about this guy. If I take the limit as n goes from 1 to infinity, -1 to the n plus 1 over n. Well, we know that this thing converges by the alternating series test. We just proved it. However, what are you doing? But we know that the sum as n goes from 1 to infinity of 1 over n diverges. Why? Because it's harmonic. Right? The harmonic series diverges. So what that says is because this guy converges, it's like a weaker convergence. It's not an absolute convergence like we had back with this guy right here. This is a strong convergence. It's like, hey man, I don't even need this guy to alternate. Because alternating, if you think about it, it increases the likelihood that a series is going to converge. Because you've got an addition, subtraction, addition, subtraction, addition, subtraction. Like in this case, I mean, it makes a very weak divergent series. Weak's the wrong adjective there, but you know what I'm saying. And it turns it into a convergent series by the alternating series test. All right? Okay. Excuse me. One more time.